Hello, we are back. So the last section, I know that was a lot to take in. I'm sorry about that. This one, I think it'll be easier because it's applications of the last two sections, the volume and surface area and perimeter, those things, and then also the converting units. So there's not really any new math. It's more just here are applications or real life situations where you would need to do that. So I thought we could talk about first, how can you approach these things? Sometimes word problems, we're given a lot of information and it's hard to know what to do with it. So I'd say, I'm going to just write little notes over here. And if you don't need this, then totally ignore what I'm saying. But if you think it's helpful, because word problems are a tough thing for you, this might help. I would say, first thing I would do is, read the problem. Read, the whole thing. Just to make sure all the words make sense and, you can kind of imagine what they're saying. And then I would kind of reread it and draw a picture. If it's kind of applies, if there's a figure that you're supposed to be finding the volume of or the area of or something, a picture, if it's applicable. Sometimes there's nothing really to draw. If applicable. And then label anything you know about it. Like if it's a circle, maybe you can draw the radius or write the radius if it's given, stuff like that. Label any given info. And then I'd say for me, I try to write down anything's given that's, even if it's not part of the picture, or if there is no picture, kind of collect all the information that you're given as far as numbers. Write given quantities, I guess, quantities for numbers. Kind of, because sometimes they're just hidden throughout the problem and it's hard to go find them, or I might forget that there was something given, I guess. And then I just try to approach, what are they asking for? What is asked of us? Because there's a lot of information given, and just digesting the information is hard in and of itself. And then it's now what do I do with that information? What do they want? Yeah, and then once I know what they want and I kind of have everything written down that I know, then it's maybe a little easier. And then, of course, you say, what do I do with this information I'm given as far as finding what they want me to find? So I'd say that's the approach. And again, it's kind of like what I said in the last video. And I don't necessarily have the whole thing mapped out as I go. I just read it and I don't really know what I'm doing necessarily. I don't see the whole thing, all of my steps mapped out, but I just approach it. Don't be worried if you don't know exactly what you're doing. I think most of us are like that. Anyway, so there's not really a lot of preliminary, theory here. We're just going to read through it and see what to do. So this first example says, Joy is planning to buy tan bark, which is just, the bark you see at parks or in some people's backyard, for a rectangular, solid-shaped portion of her backyard. So I kind of dig back in my memory. I'd say, oh yeah, rectangular solid is kind of like a dice, if I imagine a dice in a board game, except it's not necessarily square. There's some kind of box that's three-dimensional. So I'm going to draw one, because there is something to draw, I guess. There might be some dimensions that I'm given or something. And the drawing is not really necessarily for points. It's not like you're drawing it and saying, okay, I better draw it good because my instructor is going to be grading this, and they might say that's not a good drawing. The drawing is more for your benefits because it's hard to picture things in my mind anyway. Maybe your mind too. It's easier to have it see in front of me. So, okay, rectangular solid. Got that so far. And then they say this area measures 13 feet wide. Okay, I'm going to kind of draw something to that effect. Don't worry which dimension you're using. Doesn't really matter. How many? 12 feet? Yeah, I already forgot. They just said it. Really? Okay, 12 feet wide, whatever. I'll make that dimension. Okay, and then they say 8.5 feet long. Okay, I don't really know which way is that, but doesn't matter. But then I noticed they said 6 inches deep. So to me, I guess deep, if I'm thinking of something in the backyard, I guess that's like from top to bottom, huh? It doesn't really matter. It's just 3 dimensions that we've got, and it doesn't matter how you label them in a rectangular solid. If there was a cylinder or a cone, it would matter. Of course, radius and all that. Okay, so far I can kind of picture this, I guess, sort of. Just, this is something they're trying to fill with tan bark. Okay, believe it, I believe it. What is the volume of the tan bark in feet that Joy will need? All right, this is where you can absolutely go back to not the previous section, that was the converting units, huh? The section before that to find the volume. Oh, jeez, I keep using the wrong pen. The volume of a rectangular solid, it was just the 3 dimensions multiplied together, right? The width, the length, the height, and I can't remember which goes first. I don't know. It doesn't matter. Base times length times height, or length times width times height. Sometimes we use base, sometimes we use height. I want to say this is not the one we wrote before. It doesn't matter. You call these things whatever you want. They're just the dimensions. So the part A is not so bad, I think. We just multiply the three numbers given together. The volume is, and it doesn't matter what order they're in. I'm going to write all those three numbers we were given. 12 feet in one of them. Doesn't matter what order. 8.5 feet in another. 6 feet. There we go. Okay. And then I've noticed the units if it's going to be feet times feet times feet, that'll be cubic feet. Feet cubed, which makes sense for volume. That's what I should expect. That's a good thing. I must have chosen maybe the right formula, right? Let's see. I'm going to multiply those. 12 multiplied by 8.5. That multiplied by 6, I get 612 cubic feet. So I believe that's our answer, at least for that one. All right. That's a good answer, I think. I don't know. Sounds good. Okay, then they've got a part B here. That's one thing when I was a student, I remember if there's part 1 and part 2 or part A and part B, once I get one answer, I want to move on and go to the next problem, but I got to remember, sometimes there's another part. I got to make sure I don't get too excited and move on to the next problem. There might be more, and unfortunately there is. But that's okay. We're helping Joy out. She's trying to figure something out for her backyard. If Joy shops at a store that sells tan bark for $2 per cubic foot, how much will it cost her to fill the portion of the backyard she had planned with the bark? So at this point, if you already know what to do right now, okay, I'm going to multiply those two numbers, the 600, why do I keep doing that? 612 cubic feet by the number that's given, $2 per cubic foot. That's fine. Feel free to just do that. But if we want, now that we have more theory behind us with the last section, we have converting units. I'm starting with 612 cubic feet, and I want to convert that to dollars. I want to know how much is that going to cost me, I guess. So they kind of gave us the conversion there, at least for the store that we're going to, or Joy's going to, I should say. I'm not going to the store. $2 per cubic foot. So that means that 1 cubic foot is equal to how much? $2. They just said it, really, and I forgot already. So sad. So I could multiply that by, this is kind of maybe overkill. You might think, really, do I really have to do it this way? No, but it's kind of nice to, I guess, use the theory that we learned in the last section. So remember in the last section, we want to put the quantity that's given over 1 to make sure it's a fraction. And then I want to say, well, I want to get rid of cubic feet, so I got to make sure that they're going to cancel along the diagonal, the one I started with and the one I'm converting with. So this conversion that I wrote in red here, or pink, or whatever that is, I want to make sure the feet are on the denominator. 1 is with feet, and 2 is with dollars. So I guess that's going to be the way it goes. So it ends up exactly what a lot of people probably already knew to do. I'm just multiplying 612 by 2. The denominators are just 1, so they don't really contribute. 612 multiplied by 2. Oopsie, I need to go here. $1,224? Holy moly. Joy, this backyard better look good for that price. Holy moly. That's a lot. But this type of problem, feel free to just, if you write the answer, I think I'll know what you did. Yeah, but you can always use the conversion type thing. Yeah, totally up to you. It's not necessary, but it's kind of nice to use what we learned in the last section. Kind of combines this section with the last section. So that's it, yeah. There's not really too much of a way to check your answer, I guess. It'd just be read over the problem again, look at your work, make sure you kind of did what makes sense and you didn't write any numbers down wrong. That's something silly I do all the time. The number is given in a problem and I write it down wrong. It's really sad, but I do that a lot. But that's it. So just keep practicing. Hopefully between all these examples in this section, we'll kind of cover all the things that you could possibly come across. All right, I'm going to read this. Example 2, it says, a cylindrical shaped tank. Even right there, I could stop right there. I'm going to say, all right, I don't know what's going to happen with this tank. Do I really care? Not really, but I got to pretend I care for this problem. But I'm going to draw a cylinder. I don't know how tall it is. I'm just drawing just to help myself visually. It might help later. Okay, now I'm going to continue reading. All right, where were we? Cylindrical. Oh, I don't want to highlight. I want to be able to see the words too. Come on now. Hello, a cylindrical shaped tank, let's say that 5 times fast, needs to be painted. Why? Don't worry about that. Just move on. The tank's diameter is 7 feet. Okay, I'm gonna stop right there and draw it because I'm gonna forget what was 7 feet again? The diameter. That means all the way across. Oh wait, why am I using yellow? Can barely read it. All the way across from left to right. How many? Yeah, feet. already forgot the unit measurement. So anyway, or from here to here, I guess 7. Remember, diameter is all the way across the circle and radius is halfway across. Okay, got that. Probably didn't need to draw it there, whatever. You know, as long as you know what you're doing or what's going on here. Now, what else is going on? And the height is 10 feet. Okay, so it's not the height of the, yeah, the height of the cylinder is 10 feet. Got it. So from here to here. All right. So far, so good. It sounds good. All right. So what do we want to do now? First, we'll calculate the surface area of the tank in square feet. All right. So let's see. This is where, yeah, I didn't write the formulas here, but we can always go back to the previous, not the previous section, but the one before that, and then look at the formula. Okay, so I have to go back 2 sections, and I'll say, what was the surface area of a cylinder again? Surface area, cylinder, it's 2 pi RH plus 2 pi R squared. That's right. Don't feel free to look that up real quick when you're doing your homework. No need to memorize it. And then I'll look at that formula, look at what I've got in my little nice drawing over here. Pretend it's nice. I think I've got everything. 10 is the height. So I've got height 10, that's given, and then well, I don't have R, right? They want R for this formula. I have something that could give me R. If diameter is 7, radius is half of that. So I just need to figure out what's half of 7. I wish that was a nice even number. That would be nice, but no, of course it's an odd number. So this is where you could write it as 3.5 or 3.5. I think because we're probably going to eventually use a calculator, I'm going to write that as 3.5. All right. So I guess they gave me the diameter. It's not needed, at least for part A. I don't know. We'll see about part B. But for part A, I don't need diameter. It did allow me to find the radius, so that was helpful. But it looks like the radius, I'm going to replace it in the formula. Here is the radius somewhere, and then R over here, also 3.5. And then everything else I'm going to copy. There was a 2 pi in front of the R. H I'm going to replace in a second. I'll think about that. Plus, and then 2 pi times R squared to the second power. Now, what was the height again? Okay, height was 10. I'm going to replace that here for H. 10. He only appears on one part, not the other part. Yeah, okay, that looks good. I just have to be careful with my calculations now. What do we got? 2 pi times, and this is where I guess this, I'm going to do order of operations. For now, I'm going to leave this 3.5, 10, 2 pi, and then 3.5 squared. I'm going to write, or use my calculator to figure that guy out. Don't be a hero, 3.5. I mean, you could be a hero and do it in your head, but why? It's 3.5 to the second power is 12.25. Looks good. All right, now that would be, now I can, there's a bunch of multiplying. I definitely want to make sure I don't approach this plus. I don't want to add anything yet. Everything has to be multiplied. That needs to be multiplied here and then here separately, and then I can add. So what do we got? 2 pi, well, I can multiply all the numbers that are next to each other. The 2, the pi, I'm just going to probably leave as pi because I guess it didn't say, do you want an exact answer or whatever. Yeah, so I'll multiply these 3 numbers together and stick a pi next to it. What'll that be? 2 times 3.5 is 7, multiplied by 10 is 70 pi. So I got that, kind of this portion taken care of. Plus, now there's a 2 pi, oh, sorry. Dang it, I keep forgetting what I'm doing here. In that case, we're only multiplying 2 numbers there. Let's see, the 2 and the 12.25. 2 times 12.25 will give me 24.5, and then the pi is still hanging around. Now I can add those. Those are like terms. I can add just the kind of the coefficient. 70 plus 24.5 is 94.5 pi. And that's all. I mean, it's less work for me to leave it that way. I know pi is not really a nice visual answer. Like, what the heck am I supposed to do with that? But surface area would be measured in square units. In this case, we're talking about feet, so I'll write square feet. But if it was inches or some other centimeters or something, I would write square centimeters or whatever the case may be. So that was part A. There are 3 parts to this. I don't think I left myself enough room, but you know what? We'll do what we can here. Now there's a part B, sadly. If 1 quart of paint covers 90 square feet, how many quarts of paint will need to be used to paint the entire tank? Well, that's another kind of conversion-ish, sort of. Oops, I did it again. 94.5 pi square feet. That's what we found the surface area of the cylinder to be. But they're saying 1 quart of paint covers 90 square feet. That's kind of a conversion I can use. 1 quart. Oh, what the? Oh my gosh. Sorry about that. Please, I don't know what, I got to figure out what's going on with that. But please rewind the video if you need to write that down. Oh my gosh. 94.5 pi. That was our answer to part A. Oh my gosh. I really don't know how I'm doing that. I'm sorry about that. Anyway, square feet. That they said 1 quart of paint covers 90 square feet. So that's the conversion I'm going to use. Let's see. And if I'm starting with 94.5 square feet and I want to convert to, I guess they want quarts, right? How many quarts of paint? I need to make sure that this conversion here is used to where the square feet are in the denominator because I want to see them cancel. So it must be 90 square feet in the denominator and 1 quart in the numerator. So it looks like I'll be taking 94.5 pi and dividing it by 90 in the end, and I'll end up with quarts. Let's see, I'm going to try to, and at this point, maybe, I don't know, well, it's hard to say. They didn't say if they want an exact answer. 94.5, I can divide that by 90. So that's going to be, is that really just 1.05? That's so nice. 1.05 pi quarts. And I guess, yeah, like I said, if this was real life, of course, I'm not going to go to the store and say, oh, excuse me, sir, or excuse me, ma'am, I need 1.05 pi quarts. They're going to say, what the heck? Get that pi out of here. I would probably multiply it by 3.14, da-da-da-da. But this is just less work for me, right? Yeah. So that was the answer to part A. Here's the answer to part B. And there's another part C. I guess it's good that somehow my computer erased a bunch of stuff because I wouldn't have had room for part C. So here's the answer. Yeah, like I said, here's the answer to part A here. We did some surface area calculation, and then part B, the answer is here. And now we're going to work on part C. What do they say? If paint costs, so they're giving us a conversion here, sort of. Oops, at least at this store. Maybe other stores, it's a different conversion rate. $15.75, that's in dollars per quart. How much will it cost? So it looks like I'm taking the number or the value that I calculated in part B, 1.05 pi, and quarts. And I'm trying to cancel out quarts and get dollars in the end. That must mean I want dollars in the numerator and quarts in the denominator. So I'm going to take this conversion rate that I was given and create a unit fraction out of it, just like we did in the previous section. The previous what was it? Lecture video. Oh my gosh, I was gonna say music video. Oh man, you don't want to hear. If I was doing a music video, you don't want that. All right, there, quarts cancel. So really I'm multiplying the two numbers, 1.05 pi multiplied by 15.75, the dollar amount. And I get something that has a decimal that goes on and on. I'm just maybe gonna round it. They didn't tell us where to round, but I think if you round to the nearest hundredth, which is the second decimal place, that's probably good. So I end up getting, on my calculator, something like 16.5375, but that 7 would round the 3 up to a 4. So I'm going to leave it like that, plus the pi, and that's in dollars, I believe, right? Yeah, because the quarts canceled and dollars is the only units left. Yeah, and this is where, I don't know, if I was going shopping with someone and then I said, okay, let's buy this paint, hand me 16.54 pi dollars. Whoever I'm with would say, what the heck are you talking about? Why are you throwing pi in there? I would probably, replace that with 3.14, but hey, not doing that is less work for me. Leaving pi as pi, hey, why would I do more work than I have to, you know? They didn't ask for it. So sorry about the screen just erasing, but hopefully you can just kind of rewind and go back, you know. So it's a lot of work, but I think if you're ever given a problem like this, especially on an exam, you would be given it in steps. So it wouldn't just be, this problem might be very tricky or difficult if I was given the information and all it says is how much will it cost. That's a 3-step process. First, I'd have to find the surface area, like part A says, and then I'd have to find how many quarts of paint are needed, and then the cost of that many quarts. So this is probably very similar to something you would see on an exam, maybe something that would guide you through it. Here, do this, then do this, then do this. It wouldn't just be good luck with this super difficult 3-step problem. Yeah, okay. That was fun. I hope the rest of these can be just as fun, or funner, but one can only dream. Example 3 here says, a child has eaten the enough. What the heck? I don't know, don't worry about that. Oh wait, probably the should be gone, but this should be here. What the heck am I doing? The child has eaten enough ice cream from his ice cream cone. All right, I know what shape that is. I'm even going to stop reading right there. Ice cream cone. I know what that looks like. That's usually like this, oriented upright, so the ice cream doesn't melt on your lap or whatever. Okay, now I'm going to continue reading. Usually that's what I'll do. If there's anything to draw along the way, I'll just draw it real quick. A child has eaten enough ice cream from his ice cream cone so that the level of ice cream is up to the top of the cone. Okay, yeah, because usually when they give you an ice cream cone, you know, the cone's here, and then there's a little bit of ice cream on the top, or maybe a lot, depending how many scoops. But let's just say in a very convenient situation, this child has eaten just enough ice cream to where it's right at that level, right where the cone is. Okay, that's very convenient for us because we don't know how to find the volume of some random ice cream shape. Good stuff. Okay, the cone is 6 inches tall. All right, I'm going to write that or draw a little, label my cone. Okay, 6 inches tall. So something like this from here to here is 6 inches. Got it. And then what else? It has a 2-inch radius. Okay. And like in the last one, they gave us diameter. This time they're giving us radius. That's good to keep track of the difference. All right, that sounds good. Determine the volume of ice cream left in the cone in square inches. Wait, square inches? Sorry, that should be cubic inches. Because volume is in cubic. If it was surface area, it would be... Sorry about that. Cubic, come on now. Oh, wow. What am I going to do? And that's right. What are we doing? Oh, yeah. I would need to go back and look through the formulas and say, okay, what's the volume of a cone? That's right. Volume of a cone, it was 1/3 pi r squared h. Don't feel like you have to memorize that, like I mentioned before. All right, and I think we have everything, in the previous problem, was it the previous one? Oh, no, the one before that, they gave us diameter, but I wanted radius, so I had to go find it. But it looks like they gave us exactly what we need. I just got to plug everything in the right place. So here's the radius. He's going to be replacing r. Of course, that makes sense. And then we got height is going to be replacing h, and then I think we're good to go from there. Volume, oops, why do I keep doing that? 1/3, don't worry about that, pi. R is being replaced with 2, and then h is being replaced with 6. All right, now R was 2 inches, and then the h was 6 inches. Okay, looking good. As long as I'm careful here with my math, I should be okay. 1/3 pi, and then 2 squared. 2 times 2 is 4, and the inches are being squared, so technically that's square inches, and I've got one more inches being multiplied here, so I should end in cubic inches. Cubic inches, okay. In this case, I could do it kind of slowly because I've got a 1/3 I'm not too excited to see in the front here. 1/3 pi, I'm going to multiply the 4 and the 6 together. 24, there we go, and we're in cubic inches. And now if I want to, I can think of that 24 pi as over 1 and multiply it by the 1/3. But actually, instead of multiplying, I can kind of cancel along the diagonal. 3 can go into 24 8 times. So if I look at this, really all that's left is the pi and the 8. 8 pi cubic inches. That seems too nice. But I think this problem was designed to be this nice. In real life, things aren't measured perfectly, like 2 inches radius for the cone and 6-inch height is probably some weird decimal number. They were just trying to be nice here, I think. So there's part A. I think that's what they asked for, right? Yeah. The mistake of me saying they wanted square inches didn't make sense because it's volume. Okay. Okay, that sounds good. Let's see. Now, the next one, part B, let's see. They want us to figure out now, determine how much ice cream cone the child will eat. So this was how much volume it will eat. The child, act like it's an animal. The volume, I'm losing it. Surface area of the cone. All right, so this is a problem. It's just an excuse for us to use those formulas. What are you gonna do? It's really sad that they think that this matters, but it doesn't. Okay, surface area of a cone. I gotta go look back and see what the formula was for that. Surface area was pi r L, and L is length. So I guess you could use L or H for height. I can't remember which one we used. I'll just say H for height because it matches the volume formula, plus pi r squared. All right. And actually, technically, I think this problem, we're trying to force an application of what's the surface area of a cone. Technically, though, this is kind of not right because an ice cream cone, there's no cone portion at this, on the circle, right? The circle part's open. So technically, the surface area is not quite right because this portion of the formula calculates the area of that circle, assuming there's cone there kind of covering the top of this shape, but there is none. But whatever, this is just a silly application. They think this child, as they're eating ice cream, really cares about what the surface area is and all that. They don't care. Neither does their parent. The parent just knows this kid is being quiet while they eat this ice cream and not yelling in my ear. So I'm happy, they're happy. All right. So the radius, that's right. The radius is supposed to go here. I'll replace it there. It's also supposed to go here in the formula. So the 2 is going to go there. I'll go ahead and replace that. 2 inches. 2 inches. Now since this is surface area, this will be in square inches. That's probably what was meant here. This will be in square inches, not cubic inches. And then the height, let's see, was 6 inches. That's going to go in only one spot. There's only one place to put h in this formula. So I'll put 6 inches there, and then that'll be all done. What do we got here? I guess I could multiply these together. 6 times 2 is 12. Pi is still in the mix. And then it's inches times inches, so it'll be square inches. Plus, what do we got here? There's a pi, but I'm squaring the 2. 2 times 2 will be 4, and then the pi. Pi is not being squared. If he was being squared, he'd be also in the parentheses. So I've got 12 pi square inches plus 4 pi square inches. We're just adding the coefficients. 12 plus 4 is 16. I'll write that guy. Why am I having a hard time finding that? There you go. 16, and then there's a pi attached, square inches. So that'd be like me, the nerdy mom, looking at my kid and saying, do you know how much surface area there is on that cone? How much ice cream cone you're really eating? 16 pi square inches. You know how much ice cream you're eating? 8 pi cubic inches. Isn't that crazy? And my kid would be like, God, why'd I have to have such a nerd for a mom? Oh my God. But that's really the only application. All right, that was fun. In case you're ever curious, you bust that one out. Next time you go to the ice cream shop with your friends and the conversation dies down and everybody's getting bored, you could be like, check it out. I got a cool thing to show you. Bust out your whiteboard and your whiteboard marker. Would you like to know the volume of that ice cream cone? The answer will be no, but you will do it anyway because it's interesting. Let's see. Blah, 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 blah. What do we got? Example 4. A magnetic refillable water balloon has been, I don't know if you've seen those. That's like a new thing in our family. They're like these, it's a sphere, but it kind of opens up along the middle, and there's a magnet, right? There's one little magnet holding it so it can open. It's pretty cool. And then by the time you're watching this video, you're probably like, yeah, those are old. Everybody knows about that. Okay, it's new to me, okay? It opens up, and then it's like got one hinge on that side, and then it'll fill with water, and all the magnets that are along the lip of it, on both lips, will stick together and hold it, and then you can keep using them. It's so cool. Anyway, someone's making a lot of money off that. A magnetic refillable water balloon has been completely filled with water. Okay, good to know, good to know. So I've drawn, I know this looks like a sphere, basically. All right, filled with water. Oh, yeah, whatever. And if the radius of the water balloon is 2.4 inches, all right, I'm going to label that before I even, read the rest of the problem. Okay, oh, no, I don't want that. I would like to see this thing here, 2.4 inches. Probably should have drawn it bigger, but what are you gonna do? We're in it to win it. Find the volume of the water in the water balloon. There you go. That's another one where I would throw that out there to my kid. Did you know that water balloon has this many cubic inches of water inside? And they'd say, oh my God, Mom, go find something else to do. Find a hobby. It's so sad that you're doing math just for funsies. Anyway, the volume of a sphere, that's really what we need, would be 4/3 pi r cubed. I don't know why it's easy for me to remember. The 4/3 is so random. Let's see. Okay. 4/3 pi is just a constant. R, we were given. Spheres are kind of nice, huh? There's only one number you need to figure out its volume or its surface area. You don't need the height and radius. You just need radius. I like how simple that is. Okay. 2.4 is the radius. Inches cubed. All right. Well, it will be cubed. Okay. So, but my order of operations tells me I have to raise the 2.4 to the third power first before I even try to involve the 4/3 pi. So he's going to be along for the ride. He's just kind of sitting there, relaxing. But I'm going to go really what's going on is 2.4 multiplied by itself 3 times, right? So you could just type that on your calculator if you want, or actually type 2.4 times 2.4 times 2.4, or do 2.4 to the third power. Either way, you will get 13 point, let me see, 824, and that'll be in cubic inches, because the inches are being cubed also. Looks good, okay. Now, I guess I can go put that number over 1, because I see that the next thing I want to do is involve this fraction. I want to multiply a fraction by this whole number, well, not whole number, but non-fraction, it's a decimal. But I have to make that a fraction so I can kind of multiply across. You can do it all in one step if you want. You're taking that number 13.824, multiplying it by 4, and then whatever you get from that, you're dividing it by that denominator of 3. So you could just kind of do all that in one fell swoop, as they say. Or you could do it in stages. For me, I like to just do it in stages because I'm kind of nervous I'll make a mistake. Where the heck did this 9 come from? I'm multiplying across 4 times 13.825. I'll do that first. 4 multiplied by 4. The numerator is multiplied to 55.296, but I'm dividing that by 3, and the pi is just along for the ride. And then that's in cubic inches. Now I'm just going to take that 55.296 and divide it by 3. And then I should be done. Yeah, like I said, if they said approximate your answer, then I'd actually replace pi with 3.14. But they didn't say that, so I guess it's less work for me. 18.432 pi cubic inches. That's fine, you can leave it like that, since it wasn't specified that they would want either an exact answer or an approximate answer, but maybe just to refresh. If you wanted this is exact, if that was asked for. Yeah, because I think we talked about before, if you replace pi with 3.14, you're just making it approximate now, because pi isn't really 3.14, it goes on forever. But in real life, you would like an approximation. That would be 8. You're going to replace the, oh, geez, again. Why? Oh, well. Sorry about that. But we can rewind the video, I guess. It was 18.432 pi cubic inches. But that was a good answer for exact, but approximate, I can replace the pi with 3.14. There we go, times 3.14. That makes about 57.88 cubic inches. That's more practical, right? If I want to know how much water is in a water balloon, this is more practical. The pi, leaving it there, in real life, I wouldn't do that. But it's exact. That's the nice thing. Anyway, sorry about the erasing, but there it is. Okay, now here's a real life situation that actually matters. Not like how much ice cream cone is in a ice cream, or how much whatever water is in a water balloon. Here we go. This might matter in real life. Penicillin. That's a good thing. The amount of penicillin administered to patients depends on the individual's body weight. So that's why I have a nurse friend, and she said, everybody talks about why no matter what I go to the doctor for, they always weigh me first. Let me step on the scale, and you're like, why do I need to get on the scale? I just have a cut, and I need someone to clean it out or whatever. It's just because they might need to give you medicine, and they need to know how much to give you. They're not trying to shame us, okay? Anyway, the amount of penicillin administered to patients depends on the individual's body weight. So it's 1 milliliter of penicillin per 100 pounds of body weight. Okay. That sounds good. There's nothing to draw here. This is where this problem, I would say, this is probably more of an application of just the previous section we covered, the converting units thing. There's no shape. I even could draw a person laying in a hospital bed, I guess, but I don't think that helps me figure this problem out, so I'm probably not going to. But okay. The next part A says, how much penicillin in milliliters would a 55.5 pound child be administered? All right, so I think in that one, we're starting with the child that's 55.5 pounds, and I want to convert it to end with what do I want? They want how much penicillin in milliliters. So this is what I want, and this is what I'm given. So I guess what I want is some kind of conversion that maybe goes from pounds. I want to get rid of pounds to milliliters, but I think that was given in the problem, luckily, so that's good. how many, would they say 100 pounds? Yeah. 1 milliliter of penicillin should be given for every 100 pounds of body weight. There we go. So there's our conversion. It looks like we want 100 pounds in the denominator, 1 milliliter in the numerator, and that's just because I want to make sure the pounds cancel along the diagonal. There we go. So it looks like it ends up being on the numerator 55.5 multiplied by 1. Okay, I got that, which is just 55.5 over 1 multiplied by 100. And then the pounds are gone and I'm left with milliliters. Is that what I want? Yes, they did say that's what we want. So I just need to divide, but I think we mentioned before dividing or multiplying by 10, 100, 1,000, whatever number that's 1 followed by a certain number of zeros. It ends up you're just moving the decimal, how many zeros there are. So I'm going to move that decimal from 55.5. It was here. I'm moving it 2 times because there were 2 zeros in the 100. So it ends up being 0.555 milliliters. So that's probably about half a milliliter you would give this kid for penicillin. Okay. So how about an adult, though? Because that doesn't sound like a lot, but hey, I'm no nurse. Let's see, part B says, how much penicillin in milliliters would a 225-pound adult be administered? So that's interesting. We can kind of compare. Is it a similar number? Is it close? Is it much bigger? Whatever. All right, but this time it's pretty much the same. Part A and Part B are almost the same. The only thing I'm changing is that 55.5 that we started with is not the weight of the person that we're interested in anymore. Now it's 225. But really the work is going to be the same. I'm doing pretty much the same thing. I want to convert. I would like to see pounds in my conversion or my unit fraction be in the denominator so they can cancel, and then milliliters in the numerator. Same conversion. I'm still, Part A and Part B, we're doing the same thing pretty much. I'm trying to get from pounds to milliliters. So I'm using the same conversion. It ends up being pretty much the exact same problem. Not a lot of brain power needed here since I used it all in Part A. Now my calculator is going to be dividing 225 by 100 instead of 55.5 by 100. 225 divided by, why am I doing that? I was going to put it in my calculator. I just said we just need to move the decimal over. 225, even though there's no visible decimal, there's a little secret decimal here. I'm going to move it over to the left twice because 100 has 2 zeros in it. Oh, why am I putting a 0 there? 2.25, there we go, milliliters. Interesting. I'm thinking about it too hard. I guess, yeah, it makes sense. That sounds about right. You know, kind of, what's it called? What's the word I'm thinking of? Ratio-wise, because notice that the child in Part A is about a little more than 50 pounds, and the adult in Part B is like 200 to between 200 and 250. I think the adult's almost about four or 5 times the weight of the child, and these amounts of penicillin are about, the child's penicillin amount is about 2.5. Or the adults is 2.5 multiplied by the child's amount. Yeah, that sounds about right. Yeah, okay. I believe it, I guess. I would hope that nurses are very careful with that, right? Oh my gosh, you can kill someone easily by that. Anyway, not trying to bum anybody out. Let's stop talking about killing, okay? This is math. Now, I threw this example in here because I did see examples like this in other textbooks. I mean, you might see this, and this is the kind of thing I was mentioning in the previous section, where you might see conversions that are very complicated in chemistry, and it's like, I don't know if I would know what to do, what to multiply by, what to divide by, because it's so complicated. So I just wanted to make sure you know that this is a challenge problem. This kind of problem, it won't be expected of you on an exam or something, but if you think maybe you'll have to take a chemistry class someday, or you're interested in nursing, or I don't know, anything, yeah, where you're using units, I guess, of measurement, whether it's volume or, I don't know, meters or length or whatever, this might be interesting. I remember, yeah, like I think I mentioned in the previous section, the video, that I took a chemistry class and they said, oh, you should have already learned this unit conversion stuff, the dimensional analysis, and I had not, and it blew my mind, because she would just jump into these problems and say, oh yeah, look, these are easy. I'm converting this many millimeters per second to kilometers per hour, and just ran through the problem so fast, and I almost cried right there and then. Oh my God, why is she saying this is so easy? It's not easy. Okay, I definitely have some sad memories from those days, but that's okay. So this one, I want to just go over these, but don't get too worried about it. It won't be on the exam. I just wanted to talk about it, just so you know for sure that there are problems where, yeah, you can't just do it in your head, sort of. You have to really write it out the way we talked about. So, okay, in this part A, we're starting with some number of millimeters per second. Notice this is the first time we're seeing rate as the starting and ending. Let's see, with a rate. A rate is just like this per this, miles per hour. In this case, millimeters per second, or like in the part B, you'll see there's kilograms per liter or something with the slash. So the way we treat those is we start, instead of just starting with a quantity with one unit, we're going to write it as a fraction. So it's not necessary to make it a fraction like we did in the previous section. We're given this number, I have to put it over 1. It's already a fraction because it's this many millimeters per 1 second. So unspoken, that number that we're starting with there, 5.39 times 10 to the whatever millimeters per second, it's already a fraction without us even knowing. Any rate is a fraction. It's the number over 1, millimeters over seconds. Yeah, so kind of like, we don't see that very often, but if if someone says, oh, my car goes 60 miles per hour on the freeway, well, it should go faster than that, but let's say that's the speed limit. If you want to make that a fraction, that would be just 60 miles for 1 hour. If you think about it, right, if someone said, okay, if I'm driving 60 miles per hour, how far would I drive in 1 hour? Then this kind of splits it up and makes it more obvious. Well, for every 1 hour you drive, you're driving 60 miles. It kind of takes this rate and makes it look, you can kind of tell, it's more easy to comprehend, I guess, to me anyway. So that's the first thing that we want to talk about or mention here. Okay, so what do I want in the end? This is going to be tough because, like, the analogy that I used in the previous section where I'm on one side of a river and I want to cross to the other side. There are lots of stones I need to step on, and it might be kind of scary in the middle. I'm like, am I even going to make it to the other side of this river? I don't know. This one, I don't think. Yeah, we have to look back at the conversions from the previous section, but I wrote them down. I know for sure I want to go from millimeters to. Let's see. What do we say? What am I doing here? Oh my gosh. 1. Why is this looking so weird? Why is this looking so weird? 1, I guess so. Millimeter. Why does this look like a crayon? Oh, oh my gosh. Why is this looking so weird? 1 millimeter. Oh my gosh, dude. Lord. Okay, whatever. There it is. That looks a lot better. Oh my gosh. Why was that so hard? 1 millimeter is, where'd I say it? Where'd I write it? Oh, I'm sorry. It was 10 to the 6th power millimeters is 1 kilometer. Because I see that I definitely, at least the length measurements for part A, I want to start with millimeters and I want to end in kilometers. And I look back at my conversion chart that we saw in the previous section. There are 10 to the 6th power, or 1 followed by 6 zeros, millimeters in a kilometer. So I'm going to use that for sure. That's for me to get the correct length units that I want. But there are also time units that I want to change. I'm starting with seconds and I want to end in hours. So I definitely need to convert from, this was my length or distance, I guess. My converting, I definitely need to use that. But to convert the time, I need to use 60 minutes, 60 minutes in 1 hour. Not only that, I'm not starting with minutes, I'm starting with seconds. So I have to use that. And also another one, 60 seconds in 1 minute. Whew. So I think these 3 stepping stones will get us to where we want to go. I just got to think about what order to go in. And like I mentioned in the previous video, you might not see the whole problem laid out in front of you. I don't know exactly what I'm doing. I don't know how I'm going to get from here to there, but at least the first step I can take and then assess what I'm doing from there, I think is the idea. Just like in the previous section, I think the first thing I want to do is get rid of the unit I'm starting with. And I know there's a unit down here I don't want. I'm going to worry about that a little later maybe. Let me get rid of millimeters. I'm going to use this conversion here. Maybe I'll use the same color to make it easier. I want to make sure millimeters are in the denominator so they cancel along that diagonal. And we said that conversion, there were 10 to the 6th power millimeters and 1 kilometer. So far, this is looking good. If I stop now and I don't use any more conversion or unit conversions, I would be ending with kilometers in the numerator and seconds in the denominator. So if that's what they had asked for, how many kilometers per second, I'd be done, but they don't want seconds. Now my job is to use another conversion to get rid of seconds. So now this is kind of confusing because seconds, where I have it now currently, it's in the denominator. For it to cancel, I need it to be in the numerator because they need to be along the diagonal to cancel. So let me see, which conversion do I have with seconds disappearing, or seconds in it? Eventually I need to use this one because I want hours, but I need to get rid of seconds, so I'm going to use this one. And keep in mind, this is a challenge problem. This is very difficult. 60 seconds and 1 minute. And now I'm going to think about this. What units are canceling and what units are left? Millimeters canceled already. I'm not worried about the length is done. I've gotten rid of millimeters. I have kilometers here. So that's good, but the distance is, or sorry, the time is not right. If I stop now, the units I'd be left with are kilometers in the numerator and minutes in the denominator. That's not quite what I want. I need one more conversion. Unit fraction, right? That last one there, I'm gonna do it in blue just to make it different. 60 minutes and 1 hour, but which way should it go? I want to get rid of minutes, I guess. That's the thing that's creating the problem for me right now. I don't want minutes anymore, and currently minutes are in the denominator. That means I need them to be in the numerator in order to cancel. That means 60 should go here and 1 hour should go there. Oh my gosh. Now we're done, I think. I got rid of this first conversion unit, or unit fraction was there so that I could get rid of millimeters and jump onto kilometers. That's good. I'm done with the distance or the length. That's all done. Now it's time. I need to get rid of seconds. To get rid of seconds, I used this conversion, or this unit fraction, but that didn't get me where I wanted to go. I think I'm almost to the other shore of this river. I'm left with minutes. That's not quite what I wanted. Now I needed one more. Holy moly, this is a lot. Now that for me, like I mentioned in the previous video, for me that's the hard part, setting it up. Now I see the units that are left. Kilometers are the only units in the numerators. All the numerators together, every unit has canceled except kilometers. So I will be left with kilometers in the numerator. In the denominator, all units have canceled as well except for hours. And that's exactly what I wanted, I believe. Let me read it again. Yeah, kilometers per hour. Whew. That was the hard part. Now it's a bunch of multiplying. I've got this number 5.39 times 10 to the second power. The 10 to the second power means I'm just moving the decimal to the right twice. So it seems like they didn't have to write that. They could have written just 539. That would have been a lot easier. But they wanted to make it hard, but that's fine. And then multiplied by 1. I don't even need to include him, obviously, but that's fine. Multiplied by 60 again and again. So I could have just multiplied all those, but I kind of wanted to show where they came from. In the denominator, luckily, we have just a bunch of 1s multiplied together plus a 10 to the 6th power. But otherwise, I think it's all 1s. All right, so I'm going to work on that numerator. What is that guy? Let's see. What am I doing here? 539, got it, multiplied by 60, and then multiplied by 60 again. That's 1,940,400 over, and then the denominator 10 to the 6th power, that's 1 followed by 6 zeros. 1, 2, 3, 4, 5, 6. Did I count that right? Okay. And what is that? That's like 1 million? So really you're just dividing 1,940,400 by 1 million. That's just going to move the decimal over. It's 1.9. If I take the decimal of this number and move it over 6 times, 1, 2, 3, 4, 5, 6, it would be right between the 1 and the 9. So I'm going to keep everything else. Yeah, I could drop those 2 zeros at the end, but that's okay. And now I can write kilometers per hour. Whew. That was tough. Oh, man. Now I want to do it again for part B? No, like I said, this is a challenge. I just wanted to show that sometimes it is necessary to do it the long way, even though it seems kind of silly. Okay, we're going to try to do this. I might need to erase some stuff. I don't see much room. Okay. Yeah, let me see. If you want, go ahead and pause the video if you need to write more down. If you haven't written all this down on your notes, you can pause it, but I'm going to erase all this now at this point. Because we ran out of room. That's okay. I guess you can write it as we go, as I erase. Maybe I'll just erase this top part and see if we have enough room there, and then if I need more room, I'll erase the bottom. All right. Looks good. Can I make this eraser thicker? This is taking too long. Boom, boom. So anyway, the weather. How's the weather this time of year? Too hot, too cold, raining, just right, hailing, stormy, I don't know. Okay, what do we got in here? Part B, very similar, probably just using different conversions, but same idea. It's a rate, 2.056 kilograms per liter. I'm going to write it as, that means for every liter, 1 liter, I have 2.056 kilograms, but I want to end in grams per milliliter. So I want to make sure I can convert kilograms to grams. How many kilograms are in 1 gram? Okay, that's probably the volume, no, not volume. Yeah, weight or volume conversion. Weight or mass, I think. That's what we said. Weight, mass. But then the other, okay, how about the liters? That's volume. Liters and milliliters. I need some kind of conversion for the weight or mass. I'll figure that out. But I also need one for, yeah, the volume. Volume, I want to convert between liters and milliliters. Oh, those are all metric, kilograms, liters, grams, milliliters. And there's no US units. Like in the previous one, there were hours and seconds and minutes. Now we don't involve any of that in there. Okay, how many kilograms in a gram? There are 10 to the third power, or 1,000 grams in 1 kilogram, according to the previous section's unit conversion chart. Now the volume, the liters and milliliters, there are 10 to the third power milliliters in 1 liter. Does that sound right? Yeah, I guess so. All right, so those are, I think that's all we need. This was, maybe part B is a little easier than part A, actually. All right, what do I need to do first? Technically in this I know I need to get rid of liters and I need to get rid of kilograms, so you can kind of use these two conversions in any order you want. Just kind of decide for yourself, which one do I want to get rid of first? It doesn't really matter. For some reason, I think because in the previous section, we always saw we want to get rid of the unit that's right next to the number, like 2.056. I want to get rid of that first, so I just feel like that's more natural because that's what we've been doing. I'm going to use this conversion, and I want to make sure that kilograms are in the denominator so that the kilograms cancel along the diagonal. And then I guess the 10 to the third grams go in the numerator that I saw here. Okay, if I stop now, I'd be left with grams, because the kilograms canceled, per liter. That's not quite what I want. I want grams per milliliter. So I'm going to keep the G for grams. I don't want that to disappear, but I do want to make sure that the liters go away. So I'll use this conversion now. But the question is, do I do 10 to the third power milliliters in the numerator or the 1 liter in the numerator? I want the liter unit to cancel. It's currently in the denominator. In order for it to cancel, I'd have to see it in the numerator. It'd have to be opposite, along the diagonal. So for sure, it looks like I need the 1 liter in the numerator and 10 to the third power milliliters in the denominator. And I think that'll do it. Okay, let me see. Are all the units canceling that I want? I think so. And then what units would be left if I stop now? The grams and milliliters. Everything else is canceled, right? And is that what we wanted? Yes. I look back at the problem. That's what they wanted. Okay, we're good to go. Now the units are done. Whew. At this point, I usually I've been holding my breath because this stuff makes me so nervous. Am I doing this right? Kind of like crossing a river. That makes me nervous too. But now, oh my gosh, it's easy. It's like you're taking the last step from the last stone onto the other side of the river. You're good. You're golden. The hard part's over. It's 2.056 multiplied by 10 to the third power, and the numerator and the denominator is just 1 times 1 times 10 to the third power. Times 10 to the third power. Oh my gosh, are you serious? And this is what's left, grams per milliliter. Check this out. Are you kidding me? Pretty much what's going on is you're taking 2.056 and multiplying by 10 to the third power, and then you're dividing by 10 to the third power. But what's that going to do? Those are just going to cancel each other. So really the answer is that exact number that you were given, but now in grams per milliliter. Really? So the number did not change, but the units changed. This was kind of a weird problem. It happened to be that there was the same number of grams. Let's see. Yeah, the reason for that is because there were the same number of grams in a kilogram as there are milliliters in a liter, I guess. That's why. Huh. It feels wrong, right? Like but okay. Interesting. The metric system is just, I think everything is so nice and uniform. Everything, all the conversions are just a bunch of 10 to the power, 10, 100, 1,000. Just things work out that way. If you start with a certain number, like this one we started with 2.056, you'll probably see those digits somewhere. Maybe that decimal will move left or right, but it'll stay. Those numbers will stay because all you're multiplying by is tens or dividing by tens or hundreds or thousands. Whew, anyway, that was fun. But again, that example is a challenge example. I wouldn't stress about that too much. But just in case, I'm just trying to get you to buy into that. You will need to do this if you take chemistry or maybe some other types of sciencey classes. Whew. But don't, this type of example right here, example 3, not on the exam. Not on exam. So don't be nervous about it. This is just to show you, I guess maybe it's like, look how lucky we actually were in the previous section. Maybe those problems weren't that bad after all. All right, thanks for listening.